Hello everyone, this is Otsochi Wadaba from Special Maths Academy, and in today's video we'll be solving the problem 6 of the recently concluded 2023 Pan-African Mathematics Olympiad. Here we are given a triangle ABC, AB less than AC, and DEF are the feet of altitude from ABC respectively, of course. We also told that P is the foot of the perpendicular from F to the line DE, and that the second circle of BDF and FP meet again at Q. And we are asked to prove that angle PBQ is equal to angle PAD. I already have a diagram here, not complete yet because we'll be solving the problem step by step, right? So we are told that DEF are the feet of altitudes. And of course, you know that altitudes are concurrent. They concur at the autocenter H, right? So basically, we know that ADB and CF are concurrent servians, and as concurrent servians, they must induce Sever's theorem, right? And so we can easily apply Sever's theorem here to give us AF over FB times BD over DC times CE over EA is equal to 1, right? And also, let's consider the intersection points of DE and AB, right? Let's call it X. I've already indicated it here, right? So by being the intersection point of DE and AB, of course, XD and E lie on the same line, they are collinear. And also, because they're collinear, it's going to induce Menelaus theorem, right? And Menelaus theorem is going to give us AX over XB times BD over DC times CE over EA is equal to minus 1, but because we don't care about the direction, we'll just leave it as 1, right? So this is what we have. And of course, we have AF over FB equal to BD over DC times CE over E equals to 1, right? So that gives us AF over FB is equal to, if we take this to the other side, we'll have DC over BD times EA over CE, right? But then we'll have the same thing for AX over XB as well. So this is just going to be equal to AX over XB. Right, so of course from this you can get that this implies that AF over FB is equal to AX over XB, right? And of course we can turn it around to get that BX over BF is equal to AX over AF, right? And that's just the same thing. And we are good for now, right? So the next thing I would like to consider is another point, B prime, right? And B prime is the reflection of B over line FB, right? So this is B and this is line, we have B here and we have line FB here, right? So if we reflect B over line FB to B prime, let's call that B prime. Of course, whatever is here is going to be equal to, if we call this alpha, then here is going to be equal to alpha as well, right? So those two angles are equal. And also, let's consider another point, B prime right here. Now, B prime is on line DE such that BP prime is equal to B prime P, right? So obviously we have that, so not equal to parallel, such that BP prime is equal to B, such that BP prime is parallel to B prime P. So basically we have angle, the first definition tells us that, of course, angle BPF is equal to angle B prime BF, right? And of course, that's equal to alpha, right? So also, this is 90 degrees, right? Since P is the foot of perpendicular from F to DE, so we have that this is 90 degrees. So we can also get that here is 90 minus alpha. Of course, everything there is 90, right? And if you add the other side, you have 90 plus alpha. But what you're interested in now is this guy here. Since B prime P is parallel to B P prime, right? We can get that this angle here, right? This angle here is equal to this angle here, right? From parallel from the parallel lines, right? We'll get that B P prime X is equal to B prime Px. And of course, B prime Px is equal to 90 minus alpha plus alpha plus alpha. That will give us 90 plus alpha, right? So if yes, 90 plus alpha, of course, the other side is going to be BB prime P. Let me leave it as BB prime P, right? Is going to be equal to 180 minus this, and 180 minus that is 90 minus alpha. So we actually have that this is 90 minus alpha. Now, but bear in mind that BP prime P is 90 minus alpha, and also BP P prime is also 90 minus alpha, right? So those two angles are equal, right? So that's going to give us, so we kind of have an isosceles triangle there. So this is going to imply that BP prime is equal to BP, right? And that's what I was looking for all this, right? That's my reason for putting P prime there, to just get that BP prime is equal to BP. Now, also since we have this kind of an angle bisector, right? Since B was reflected over FP, so we have an angle bisector there, right? Here's alpha BP prime F is equal to alpha, and B prime PF is equal to alpha as well. So we have an angle bisector here, and then the angle bisector theorem is going to give us that from the angle bisector theorem, we'll get that B prime F over BF is equal to B prime P over BP, right? From the angle bisector theorem. And of course, I've already established that BP is equal to BP prime. So we can put this as B prime, or sorry, B prime P over BP prime, right? So basically we have this here over this here, right? But then if you look closely, you see that we have similar triangles there, right? It's because of these parallel lines. Those parallel lines will induce similar triangles. So basically we have that triangle B prime PX is similar to triangle B P prime X. Of course, this angle remains the same, and then we have these two angle. This angle here is equal to this angle here, as we have already established here, right? So that's enough to induce, or that's enough to conclude that those two triangles are similar. And then we can use this here as well, right? Because that's going to imply that B prime P over BB prime is equal to B prime X over BX. So from this, all in all, we can get that B prime F over BF is equal to B prime X over BX, right? And of course, that implies that we can phrase it this way: B prime F over B prime X is equal to BF over BX, right? We are just turning things around. But now remember that I've already gotten that BF over BX or BX over BF is equal to AX over AF, right? The same thing as BF over BX is equal to AF over AX, right? So we have this, right? So we can just attach that here. We can attach that here to give us equal to AF over AX. Now, there's a very nice theorem in Math Olympiad called the Apollonius theorem. And what the Apollonius theorem is telling us is that if we have segments, let's call it here we are using fx. So let's say for any segment fx, the locus of points, let's say the locus of points, right? H, let's not H again. The locus of points, let's say J, such that JF over JX is equal to some constant, right? Or just that the locus of points such that JF over JX is equal to some constant is actually a circle, right? So now we have 3 points here. B prime F over B prime X equal to BF over BX equal to AF over AX, right? So there are 3 points there, B prime B and AX, that supposedly lie on that locus, right? And that's the locus such that, and Apollonius theorem is telling us that that locus has to be a circle, right? The locus of points, let's say J, such that JF over JX is equal to a constant. They're all equal, so we can equate it to a constant, let's say T, right? We can equate this to a constant T. And Apollonius theorem is telling us that the locus of such points is a circle. So by definition, we expect B prime, B, and A, and B prime, B, and A to lie on a circle, right? But now we have that B prime, P, and A actually lie on a line, right? So they all lie on a circle and they all lie on a line, right? But a circle and a line can intersect at most 2 points. So basically, all in all, what this is telling us, or what Apollonius theorem is telling us here, is that at least two of these have to be equal, right? Because we can have 3 different points all lying on a circle and all lying on a line, right? At least two of this has to be equal, right? So just make that 2 points, right? And those 2 points will be the intersection points of the circle and the line. But now we already know that B cannot be equal to A. We have a triangle there, so B is definitely not equal to A. We also have that B is not equal to B prime by the definition of B prime, right? B prime is a reflection of B over FP, and B does not lie on FP, right? So B is definitely not equal to B prime. So that's just going to imply, or what we can induce from here basically is that B prime is equal to A, right? And that's the point of bringing B prime in the first place. So we have that these 2 points are actually equal. So basically, since B prime is equal to A, since we got that angle BPF is equal to angle BP prime F, we can just replace that here. We can replace this with angle APF, right? So basically, we have that BPF and APF are equal to alpha. So that FP is actually bisecting angle BPA, right? And that's what I was trying to bring out here. I'm trying to bring out FP is actually the bisector of angle BPA, right? So, and Apollonius theorem helped us get that. So now let's go into our main proof, right? Now let's go into our main proof. I think we have enough, or we have what we need to finish this problem now. So basically from now what I'm able to establish so far is that angle BPF, right, is equal to angle APF is equal to alpha. I would like to indicate that there, but I can't because of that part there is a bit tiny, right? So of course, we haven't forgotten Q, right? Q is actually the intersection point of the second circle of BDF and the line FP, right? So of course, we know that BFQD is cyclic, right? So we have that. And since BFQD is cyclic, we can get that angle FQB B is equal to, or angle, let's call it angle BQF. Right, you can get that angle BQF. Of course, we have that opposite angles in, we have the opposite angles facing the same arc in a cyclic quadrilateral or in a circle are equal. So you can get an angle BQF is equal to angle BDF. Now we also know that we also know here, of course, this D and F are the feet of perpendiculars. Let's not forget that. So actually what we have here is kind of here's 90, and I won't draw the full length, but if you put this something like this going all the way to C, we have that here is 90 as well, right? So technically we have two angles facing the same side AC, two angle 90s facing the same side AC. So of course that means that ACDF is cyclic, right? ACDF is cyclic. Generally, when you have attitudes that way, just know that there are a lot of circles involved, and this is one of them, right? ACDF is definitely cyclic. So and by being cyclic, we have this, right? ACDF. We have this being cyclic, right? So technically, of course, you know that the opposite sides of a cyclic quadrilateral sum up to 180. So basically, if you mark this A, this is if this is A, we expect here to be 180 minus A, and of course, this other side will be 180 minus that, which is back to A. So of course, we have that angle BDF is A, right? So that's also telling us that angle BQF is equal to A, right? So basically, we have angle BQF is equal to A, which is nice because Q was kind of flying before now. All we knew about Q was the intersection point of BDF and FE. So at least we have gotten something nice about Q. So next thing we want to see is that let's look at this BDEA. Of course, similarly to AC or similar to ACDF, we have angle 90s facing each other here, right? I won't go the full length so it won't confuse the diagram. We have another angle 90 here, right? So obviously we have angle 90 facing the same side AB here. So of course that's going to imply that BDEA is cyclic, right? BDEA is cyclic, right? And that being cyclic implies that angle ADE, angle ADE is actually equal to angle ABE. And of course, this is 90, this is A, so whatever I say is going to be 90 minus A, right? So that's 180 minus 90 minus A. Remember that this is a full line here, so that's going to be equal to 90 minus A, right? And that is, so that like definitely we have that this angle here is equal to 90 minus A. But then P is the foot of perpendicular from F on DE. So here we have another right angle here. So here is 90 minus A, and here is 90. So technically we have that here is A, right? So basically we have that angle PTD is equal to A. So this implies that angle PTD is equal to A. So I think with this, we can actually finish this problem with this. Remember, we are asked to show that angle PAD is equal to angle PBQ, right? So technically, angle PAD, right? We can call it angle PAD, right? Of course, it's equal to angle PAT, the same line, right? So we are referring to this angle here. And of course, this is an external angle here. And of course, this is an internal angle. So basically, generally, of course, we know that when we have a configuration like that, we can get that angle PAT is equal to angle PTD minus angle APT, right? So we can get that angle PAT from the theorem of external angles. Like generally that configuration with external angles, we can always establish that this is equal to angle PTD minus angle APT, or of course angle APF is the same line, so it's the same thing, right? Or let me just equal to APT equal to angle PTD minus angle APF. And of course, I've established that PTD is alpha, and you have established that PTD is A, and you have established that PTD is alpha. So this is going to be equal to A minus alpha. Also, do the same thing for PBQ. We get that angle PBQ, angle PBQ is equal to, we're also going to use external angles now. We're also going to use external angles, right? So we have already established that FQ, that BQF is equal to A, right? So okay, let me take that. Right. So I've already established that we are going to do the same thing with some similar with external angles. We have already established that BQF is equal to A, and then we have already established that BPF, right, is equal to alpha. So similarly, we are going to get that. Similarly, we are going to get that angle BPQ is equal to A minus alpha, right? And that would be a problem solved, right? Just the same, we have that we have already established that BQF is equal to BDF, which is equal to A. Here's A. And then I've already gotten that BPF is equal to alpha from here. So we have that this is alpha, right? So technically we have that from the same external angle configuration, we have that angle BBQ is equal to angle BPF, sorry, is equal to angle BQF minus angle BPF, right? Minus angle BPF, which is also equal to A minus alpha. And with this, we are done. We have that PAD is equal to A minus alpha, and that's also equal to angle BPQ. So we get that angle PAD is equal to angle BPQ, right? And with this, we are done. This was what we wanted to show from the beginning. And with this, we are done. So thank you for watching this video. See you in the next